The lesson today is on biconditional statements, writing a good biconditional statement, and we're going to throw a couple of definitions in there. So let's start, of course, with our essential question. What is a biconditional statement? And when can I write one? You can't always turn things into a biconditional statement, so we'll learn how we can. Let's start with these little definitions that we wanted to talk about. Two lines that intersect at a right angle, or to form a right angle, of course, are perpendicular lines. Been knowing that for a long time. Perpendicular lines, and we know this is the symbol for perpendicular lines. Also, if we're looking at a figure and we see that we have the little box there, then we know that those lines are perpendicular. And the statement, and this is unrelated to perpendicular lines, I'm not really sure why this is thrown in here at this point, but the statement that contains the phrase if and only if, that's your biconditional statement. A biconditional statement is a single true statement that combines a true conditional statement, a true conditional, and its true converse. As always, we'll do plenty of examples so you know what's going on here. A definition is good. Okay, so how do if I wanted to write the definition of something, how could I look at that definition and decide whether it's a good definition? Well, it's a good definition if it could be written as a biconditional. For instance, let me just make one up. A writing instrument. Well, let me write the definition first. Let me write the definition. A pencil, let me try to think of a definition of a pencil, and then we'll decide if we can write it as a biconditional. If we can, then it's a good definition. A pencil is a writing instrument with lead and an eraser. And yeah, I know they don't all have erasers, but a standard pencil has an eraser. Okay, so let's try to write that. Let's try to write that as a biconditional statement. So as a biconditional statement, I would say a writing instrument is a pencil. And remember, it's got to have if and only if to be a biconditional statement. Is a pencil if and only if it has lead and an eraser. Okay, and we use two symbols for if and only if. We might use this symbol, a thick line that's got arrows on both ends. That would be if and only if. And then sometimes you'll see it written like this, IFF, if and only if. So let's see, is that a true biconditional? A writing instrument is a pencil if and only if it has lead and an eraser. Well, how do we know if it's good? If we can turn it around backwards and it's still true. So if a writing instrument has lead and an eraser, if and only if it is a pencil. So yeah, that's true both ways. So that is a good definition of a pencil. So anytime you're looking at the definition or you're trying to make a definition of something, be sure that you see if you can write it as a biconditional, and then you know it's a good one. All right, here's some other examples. We got a biconditional statement that says an angle is a straight angle if and only if its measure is 180 degrees. Rewrite it as a conditional statement. Okay, if an angle is a straight angle, I'm going to use my angle symbol there, then its measure is 180 degrees. Okay, if that's my conditional statement, then the converse of that must also be true for the biconditional to be true. So what is the converse of this? Well, let's switch the hypothesis and conclusion. If an angle's measure is 180 degrees, then the angle is a straight angle. That's true, right? Of course that's true. So the conditional is true, the converse is true, therefore we can write it as a biconditional statement. All right, why don't you try this one? Pause right here, come back and see. All right, I think we should answer this question here last after we rewrite this as a conditional and then write its converse. So a square is a figure with 4 right angles. If I write that as a conditional, it says if a figure is a square, then it has 4 right angles. All right, easy enough. If I write the converse of that, if a figure has 4 right angles, then the figure is a square. Is the conditional statement true? Yes. If a figure is a square, it definitely has 4 right angles. Is the converse true? If a figure has 4 right angles, then it is a square? Of course not, because it could be a rectangle. Therefore, the conditional and the converse are not both true, so I cannot write a biconditional. So let me come back over here and fill this in. No, this is not a good definition. Not a good definition. Why or why not? Because the conditional, well, let's just say because the converse is not true. Conditional and converse must both be true in order to write a conditional statement. And this is saying the same thing here. You can only write a biconditional statement if the converse of the conditional is true. So if we want to write a biconditional, write the true conditional statement. Write the converse. Decide if the converse is true or false. And guess what? If it's false, you can't do it, can you? You can't write a biconditional. If the converse is true, write the biconditional statement with if and only if, remember. If the converse is false, then of course you must provide a counterexample, just like we did above. All right, let's see if we can do these. If possible, write the following statements as biconditionals. If not possible, of course, we got to provide a counterexample. So our biconditional would say the square root of x equals 1 if and only if x, I don't need a comma there, if and only if x equals 1. All right, so let's think of this the other way. If we turn it around and say if we say x equals 1, if and only if the square root of x equals 1, is it true that way? Or we could think of the converse. The converse of this statement here says if x equals 1, then the square root of x equals 1. the conditional is true, the converse is true, so this is a good biconditional statement. How about this one? If two angles are vertical angles, so let's do this. Two angles are vertical angles if and only if they are congruent. Well, that sounds right, but let's write it backwards and see what happens. Two angles are congruent if and only if they are vertical angles. Well, that's not true, is it? We can come up with a counterexample, right? How about this? How about if I just take perpendicular lines here? This is 90 degrees. This is 90 degrees. Those two angles aren't vertical angles, are they? So this is not a biconditional statement. I mean, it looks like one, but it's not true. It's not a true biconditional statement, so we can't write that as a biconditional statement. So that would not be a good definition of vertical angles. Right? How about the last one? If two angles are supplementary, then the sum of their measures is 180. Two angles are supplementary if and only if the sum of their measures. A lot of writing in this unit. Sorry about that. Is 180 degrees. So how do we decide if that's a good biconditional? Let's say it in reverse. The sum, let me see if I can do this. The sum of two angles measures is 180 degrees if and only if the two angles are supplementary. That's true, right? And if I wrote the converse of this statement right here, it would say the sum, it would say if the sum of the measures of two angles is 180, then the two angles are supplementary. So, yep, that's a good one. That is a biconditional statement. Therefore, that's a good definition for supplementary angles. And let's try to do this one here. Maybe pause here and then come back and see what we did. Go. All right. I hope this is what you did here. You wrote your conditional statement, which says if an integer is divisible by 100, then its last two digits are zeros. And then when I write the converse, it says if the last two digits of an integer are zeros, then the integer is divisible by 100. Is that a true biconditional statement? Yes, indeed it is. So there we go. Write your summary. Have a good day.